Hey guys, this is the second video looking at kinematics on the Mech 2 EdXL syllabus. Here we're looking at where we're integrating and differentiating. Generally we have variable acceleration, and so we cannot use the constant acceleration equations. Right, particles move in a straight line with this velocity as a function of time. What is its acceleration when instantaneously? Good word. At rest. So it's at rest when its velocity is 0, i.e. this is 0, and all I've done is just changed all signs of all it, effectively moved it over to the other side. And if we solve that, we get these two times. We do not have a time machine, so let's ignore that one. So at 6 seconds, it is at rest for a tiny amount of time. We need to find an equation for acceleration because we want its acceleration when it's at rest. And what we do is we have velocity. We want to find acceleration, so we go down and we differentiate. So differentiating that, we get -1 and -2t. Let's put that t equals 6 into our acceleration, and boom, we get -13 meters per second. So really, these sorts of questions are about following this. Go up from acceleration to velocity to position and you integrate, go down from position to velocity to acceleration and you differentiate. Okay, particles moving in a plane. Looks all scary with the I's and J's, but isn't. Just do exactly the same sort of thing. So it tells us when t is 2, p is at 9. It's telling us that because it knows that we're going to get a constant of integration, and we'll need two values at the same time to be able to find that constant. Okay, find the distance from the origin when t is 0. Right, I've got position, I need velocity, so I've got velocity, I need position, so I integrate velocity to get position vector. And I integrate this, and I get that, integrate that, integrate that, integrate that, and then I have the constant of integration. I know these two things from here, so I put them into here and rearrange, and I get this as the constant of integration. And all I'm then doing is incorporating this back into these two, the j bit 5 into there, and the 12 bit I into there. So I now have an expression for my position vector at any time t. So when t is 0, put t is 0 into this, and I've got -12i plus 5j, distance of 13. Boom, done. Acceleration of a particle when an instant is moving parallel to I. If it's parallel to I, its j component is 0. So all I do is I just put from its velocity vector the j component to be 0, velocity vector here, j component is 0, and I get time of 2/3 of a second. I differentiate v again here, differentiating v, so that'd be 6t plus 6ti plus 6j to get acceleration, and I then put my time of 2/3 into that and get my acceleration when time is 2/3 of a second. Okay, final one. We also use this kind of malarkey when we're dealing with forces. So we have here the displacement of a particle, and we've got a force acting on that particle. So this is all about trying to get the acceleration so that I can then incorporate F equals ma, my second favourite equation. So I know the displacement, I want to get the acceleration, so I differentiate that to get velocity. I differentiate velocity to get acceleration. I then put t is 4, because that's what it says, into the acceleration, and I know at time t is 4, the acceleration is -4 meters per second. It wants the magnitude of the force, so all I do is put 4 into F equals ma, and boom, I get 0.8 newtons. Tiny little force. Okay, I'm done here. Stick a fork in me. Goodbye.